My talk is about making AI useful and usable, and it'll all be about how humans can work with machines. So this is the kind of data generating process that I'm interested in. This is an actual patient in the neurological ICU at Columbia. And this is what my collaborator sees when he walks into the ICU. It's kind of an HCI disaster. You see lots of different monitors, they're disconnected. It's really hard to spot patterns and figure out what's going on. And it's a complex and high stress environment. So it's actually really important to spot these connections. This ICU is somewhat unique in that they actually store the data. A lot of ICUs don't. I had collaborators also in pediatric intensive care at Columbia, and there either you happen to see something useful or a nurse writes down a number that might be important, and that's it. Once it's measured, it's just gone forever, which is sort of surprising as a computer scientist, right? That there's all this really interesting data and no one keeps it around. The problem has been that a lot of ICUs don't really see the value of it clinically. They don't really see how it could be used for treating patients better because computer scientists haven't really given them a lot of good use cases. The problem has been a lot of the computer science solution has been alarms. And so basically we go in and we figure out, okay, we can tell doctors a bad thing is happening. We can maybe predict this bad thing and we'll signal an alert about it. And of course, what happens is this is an ICU. A lot of the patients are really critically ill. Lots of bad things are happening. And the vast majority of alerts that the doctors receive are not actually useful or actionable. Something like 90% are not actually actionable. One of the solutions has been creating different sounds for the alarms. And so if you make maybe like a really important one sound different from one that's less important, maybe the doctors will follow it then. Doctors and clinicians couldn't really tell the difference between these different sounds, so that was a failure. And in the worst case, there have been alarms that actually should have been followed because they were important, that weren't, and patients actually died as a result of this. So it's a major failure as a computer scientist, I say, on our part, to really figure out what the doctors need and what's useful in this environment. Now, as a person who's spent most of my career looking at causality, I think clearly this is the problem of wanting to know about why. We've been telling the doctors what's happening. You know, here's an alert, this patient's in a critical state, their brain is swelling or oxygen is low, but they actually want to know what actions they can take. And so what can they do about these things that are happening and which ones are modifiable? So not everything can be, you know, fixed or changed. And in that case, maybe an alert is not useful. On the computer science side, if you've heard about AI, machine learning, and health, a lot of the work that's been in popular press has been about deep learning. And so this is not at all about why or causality. It's about finding patterns in data, right, and making predictions. And often these systems seem to be doing a really good job of making predictions. And so they're winning contests, or you see headlines that AI is better than a radiologist, or it's going to replace radiologists. 2021 is an exciting year for me because I've been waiting since 2016 to use this quote from Jeff Hinton, when we can say conclusively that it's wrong. So in 2016, he said that, and actually he said it in a much more colorful way about we're like the road runner that's going off the cliff and we haven't looked down yet. But that it's just totally obvious. Deep learning is better than radiologists. You know, you don't need to train anymore because deep learning can get more experience. And what he means by experience is that these machines can take in lots of data, right, from images. They can look at many more than a person can, which is true, but they don't really have the background knowledge that a person would to really understand this data in the way an individual could. And so people can learn from far less data because we can draw on other knowledge that we have. And so we don't necessarily need data, which is kind of a feature of humans. We can draw connections much more quickly. And then eventually he concedes that, like, you know, maybe we need more radiologists then, but there's enough now, so you still don't need to train anymore. On the other hand, there have been other cases looking at specifically radiology and these methods that have done really well in data, but when you look at how they're actually getting these results, you find they're getting the right answer, but in the wrong way. And so this was one example where for detecting pneumonia, methods were using chest x-rays. They had good results, but if you look on the left where the numbers are telling you how important each area of this x-ray is, and so one means this is really important for the algorithm, the parts that are really important are telling you this is a portable scanner. And what kind of scanner you use doesn't have anything to do with whether you have pneumonia or not, right? If you switch the scanner, it's not going to affect your probability of pneumonia, but for the algorithm, it will. And so again, this is the thing, a person wouldn't need to see thousands of x-rays to figure this out, but algorithms do. Another of my favorite examples is from Google. So this was someone who used to work at Google, who again said, you just need to know if something works. Why care why it works, right? And in fact, Google had a really well-publicized failure. So if you've heard of Google flu now, it's been in kind of lessons learned negative sense. At the time, Google flu was like the first big data success story. They were using search queries to figure out when cases of the flu were happening and to actually detect it faster than the Center for Disease Control. Of course, now we can appreciate a little bit more how important that is, early detection. And so that was really exciting. And then on the other hand, a couple years later, it just completely failed. It started predicting twice as many cases as there actually were. And it's because there's no causal link between what you search for and whether you have the flu. You might hear news stories about the flu. You're searching for another person, you hear about Google's research, and then maybe you start searching for it, right? All these things happen. And so the common theme in both of these cases is that, yes, you can get good results with machine learning and AI, but you can't really predict when these things are going to fail, right? They're not robust. They're brittle. They're susceptible to these sudden dramatic failures that, if you're working in industry, end up being well publicized and somewhat embarrassing. So this was what ended up happening with Google flu. It was predicting twice as many cases. That was bad. So the argument you often get about machine learning is, if you only need predictions, you don't need causation. Correlations are enough. And I hope to convince you that even if all you care about is prediction, if you want robust predictions, correlations aren't enough. And explanation, right? If you want to know, why these things seem to be related in your data, there's a website that crawls the web for time series that seem to have similar patterns. A lot of them involve cheese for some reason. I don't quite know why. Of course, if you search, for any time series, you're going to find two. Maybe they're both exponentially growing, something like that. I found Starbucks stores and autism have the same pattern, but there's no link between these things, right? I can make up stories for some of them, but there's not actually, one causing the other. And so again, we're getting the right answer the wrong way here. So my work has been primarily about learning causal models. And so instead of finding just predictions or correlations, learning about why things are happening and doing it from really difficult observational data. And so looking at heart failure from people's medical records, which lets you go backward to see what's happening before people get sick versus having to look prospectively, and wait for people to develop illness. You can use their records and see what happened. Using data from sensors people wear in daily life to understand individualized causes of risk factors with diabetes. And then I'll tell you a little bit about stroke in this talk today. So in stroke, I started off when I was in high school. I did biomath. I've always done some form of biology and computing, looking at structural properties of DNA. And then in college, I was in a bioinformatics lab. And I stayed there for my PhD. We looked at activities of genes, so what they were doing over time, how they were expressed. And then when I was graduating, I heard about electronic health record data. And I thought, well, this is very exciting. You have a huge amount of data. You have, records for maybe 20 million people in a hospital system over decades. And that sounded great. And so I did a postdoc at Columbia. And what you realize once you look at the data is how much of it's missing. And so you might have 20 million people in your system, but if you're in New York City like me, you might go to 4 different hospital systems. Lots of people move in and out of the area. So you don't have people's whole life histories like I'd sort of hoped that you would. You have fragments of their histories. Lots of people don't have medical care or don't have proper access to care. So there are all these gaps and things that are missing. So ICU was kind of a nice case where you have people who are in the ICU during their stay. You have all the data during their stay. All. We'll get to, it's not quite all. But you don't really need to worry. If someone's had a stroke, what's happening during that recovery is a lot more important than what happened 10 years ago. So it's a really interesting data set for causal inference, looking at what was happening during recovery from stroke, after brain injury. And the doctors I worked with have all this interesting monitoring that a lot of other ICUs don't. And so there are probes into the brain, they have EEG on the surface of the brain, they have physiologic measurements. So that was really cool. Back to the missingness, even though people are in the ICU and are sort of a captive audience, doctors measure different things for different people. And so when I've showed this to people who focus on theory, they say, why would you ever use this data? this is terrible and crazy. Like, it's just hopeless, give up. This is the reality of the ICU, right? I have no ability to influence medical processes. Doctors are going to measure what they think is important. It's less critical in the ICU, but in other scenarios, what's measured also depends on people's health insurance. And that's just the reality of, the healthcare system, particularly in the US. And so if we can't use data like that, then we can never learn from, the healthcare system. So these are 3 patients, monitoring changes over time. The middle patient had variables that are measured hourly. And it's hourly because a nurse writes down the number every hour. And you can see the lines are not evenly spaced. And so they get busy, things happen. These are not exactly every hour. And so I started working with this data in 2010. We spent 5 years developing methods to address missingness. If you ignore the missingness, then you're going to find incorrect causal models, because whether a variable is there or not, it tells you both what's happening with the patient and also what the doctor thinks is happening with the patient, right? The severity matters a lot. You're not going to have invasive brain monitoring in someone who's conscious. And if you ignore that, you're going to find incorrect causal relationships. So we spent a lot of time solving these other problems that I was less excited about versus causal inference, but that had to get solved. Finally, we found a causal model. This was super exciting. After dealing with missing data and all these other problems that cropped up, we had a causal model of what was happening during recovery. And so these were 2 different time periods after someone's stroke. And the important things were that both the number and actual cause relationships changed over time. So there were more later on during recovery, and specifically causes of brain swelling, which confusingly is TW% for reasons we don't need to worry about. The causes of that were different. So early on, it's brain temperature. Later on, it depends on blood flow and oxygen. And what's interesting is if the causes are changing over time, then maybe your treatments also have to change over time. So this was a success story for me. But when I showed this graph to my collaborator, he called it an unholy mess. He was much less enthusiastic about this. And so that was initially extremely disappointing after 5 years that he was not immediately seeing, the promise of this. And we talked through it for a few hours. And the reason was there's a disconnect between what he's trying to do and what these causal models are showing him. So here it's showing, heart rate causes this and that. But the interventions he has are medications and surgeries and things like that, right? He doesn't have a control knob on heart rate or brain temperature. He can give a medication that can maybe influence these other things, but he can't directly control the variables, right? And this is telling him what would happen if he could do that. So that starts making me worried about causal models, because generally we focused on learning larger and larger networks from data, and haven't really focused on how well people can use them to do actual tasks. In the last few years, I've been collaborating with cognitive scientists on decision-making from causal models. So if we look at how causal models are evaluated, usually evaluations look like this, and they all boil down pretty much to how many of the causes that are really there do you find, how many wrong causes do you find. Sometimes we look at how much data you need or how fast your method works, but it's all the idea that more is better. If you find more causal relationships, your method is better than mine. And we don't worry about, do you find things that can be modified, right? So family history for diabetes is a risk factor, but not actually a useful one to know about because you can't change it, right? If your interest is actually modifying your risk, that's not a useful thing for me to tell you about. We don't worry about strength or timing. Do you find causes that act sooner or later, weaker ones? None of that's captured in these numbers. So it seemed like a big gap. When I looked at work in psychology, there's a lot of positive news. People actually can make decisions with causal models and they can use them to do tasks, but the tasks were really unrelated to anything that you see in daily life. They were, if you have these mind-reading aliens and you want to send messages from one alien to the other, which alien should transmit the message? Or, these pencils and blickets. And so if you want to make something light up, which thing do you, turn on? And so people are really good at that. But it's really different from, again, the kind of information I'm giving my collaborator, where he already knows a lot of stuff about brain swelling and heart rate and these other variables. It's not like aliens, right? He's not learning everything he needs to know from the model I'm giving him. He's combining it with his existing knowledge. So I started doing these decision-making tasks in everyday situations. So not aliens, but things like managing your weight. So one of the examples was a new college student wants to avoid gaining weight. And you get a simple causal model, and we ask, for some choices to give the person. And so it's a realistic scenario. We expect people whether, they're interested in losing weight or maintaining their own weight. They've thought about weight and diet and nutrition at some point in their lives. And it sort of thought like, even if you know the right answer, maybe, the model will prompt you to remember it. It'll be a sort of net good. That was not what we found. The bottom line was causal information was worse than nothing. So if you're glass half full, like people are really good at answering these questions. They had really high accuracy, 89%, that's great. But it dropped to 80% when we gave them causal information. If you're interested in visualization, you might say maybe there's another way to present the information. I think that's a huge open problem in causal inference and causality. We don't have a good way of conveying these results. But we also give people text and the results were the same there. And so it's not just a matter of how we give them the information, it's the information content itself is somehow making things worse, which was, again, disappointing a little bit after 10 years of work trying to get causal models. We give people causal models and they make bad choices. Tested this in lots of other scenarios that I won't show you, looking at personal finance, diabetes, things like that. And once we started separating out into cases where some people had prior knowledge and others didn't, like about managing type 2 diabetes or type 1 diabetes, we saw an interesting effect that it was only in the cases where people had some experience and familiarity that they did worse. So if people knew nothing, they treated it like these aliens problems. But if they knew something, it was more like Tetris, where you have to combine what I'm giving you with what you already know. And then sometimes you have a hole in your mental model, and my information fits perfectly into that hole, and then you can answer the questions well. Other times it's really awkward, and you're not really sure how to piece it together, or you started second guessing yourself. And so we did tons of follow-up studies with thousands of participants online. We found that people's confidence was getting crushed with this information. Some people would start off thinking they know something, we give them information, then they start thinking maybe I don't know so much at all. We did other things trying to manipulate how much people think they know. Often we're really bad at knowing when we need information and knowing what knowledge we possess. That worked a little bit. We were able to sort of inoculate people against the negative effects of causal information, but we're still not able to make it better than nothing, which was, again, quite dispiriting. And so after a couple of years, in the last few months, finally, we've been able to make causal models useful. So it's much more exciting giving talks now where I actually have a positive result. After a couple of years of, I only have bad news, causal models are making things worse. And so far, I don't know how to make them better. And so the way we've done that is by focusing on what matters. So versus giving people everything, giving people really tailored information. And so if we have a complex model like this is one created in the UK about obesity. It's very comprehensive. This is kind of like what computer scientists create from data. It gives you all the things that influence weight and obesity, which is great. You learn a lot about the problem. It has social factors, diet, environment, all of that, but it's really overwhelming if you're making a decision, right? And you might not be able to modify all these things when you're making a choice. And so in these experiments, we've been creating simplified models that present only what's needed for the right answer. And so if we give people just the path that targets the correct answer for each question, we tested how well they would do compared to the complex diagram. And we tested this in lots of domains, but I'm just going to show you one here. So this was still about weight management, but we've tested about things like reducing your carbon footprint, donating to charity, keeping employees satisfied, saving for retirement, lots of things about society and life, finances, health. We had one about COVID, another about mental health, and it worked the same in all the different domains. And basically what happened was with the complex diagram, people have the same results as if you give them nothing. They either don't know what to do or they kind of ignore it pretty much. But if you give them a simple diagram that contains nothing extra, just the stuff for the right answer, now finally these causal models are useful. And more recently, we've tested this if we add back in a little bit of extra information. So we added in information that contradicts one of the answer choices. So you have a choice like maybe someone should quit their job. In the model, we tell you, in fact, that financial stress is really bad for mental health. And so you would think that would push them even more strongly to the right answer because this is telling you the opposite of what's in the choice. And no, the results get bad again. And so once we put in anything that's not needed to pick the right answer, people start doing worse on these questions. Yeah, it also affects what choices people pick. This is an interesting example of how you present information really affects people's preferences. So if you have a chain and each link isn't deterministic, your best bet is to intervene the most direct way on an effect, right? So if I prevent you from seeing food ads, maybe you'll have a healthier diet. But if I can, tell you to have a healthier diet directly, that's obviously more effective. But in fact, if we give people this diagram, they're much more likely to target food ads. Whereas if we give them the whole model or they use what they know, they pick the healthy diet. So simplicity can also have unintended consequences. It's been interesting seeing how significantly the presentation of information and the information we give people and what we leave out influences their choices. So I'll wrap up quickly and say I've learned over the last few years, know your users, right? Be humble as a computer scientist about what you can do and what people actually want. I won't get into it at all. So I realized my collaborator mostly wanted to know about consciousness. And so we started looking, instead of causal relationships, we started looking at can we detect people's degree of consciousness without brain monitoring? And we've done it from physiologic variables. So this was a paper looking at the relationship between different variables and how the time lag changes based on degree of consciousness. And then since then, we've actually developed algorithms to classify people's degree of consciousness in a fully automated way, which is a thing that's actionable that the doctors can actually use. They can use it during rounds to augment what they do, which takes about an hour to assess an individual, or they can use it in between their assessments as an extra data point, where normally this can only be done once a day, the assessment, because it's really time consuming. Now we can give them information in between those assessments so they can actually see changes in consciousness. And so we got there by realizing, Dave was saying, right, the users are people. We're not at the point of fully automated decisions by computers. So a person's going to have to use our work at the end, and we need to convince the person, right, that we're giving them information that's reliable, that's useful. I like to make a pitch for usable AI versus explainable AI. So when we're working with domain experts, the idea of what's explainable has generally been targeted towards machine learning people. The doctors are not going to understand the idea of features in a model. Something that's explainable for a machine learning practitioner or expert isn't really explainable for them. And also being explainable doesn't mean that it can help them do a task, right? And so I'm much more interested in, can we evaluate utility of a causal model, of an algorithm for a person doing a specific task, not just, is it accurate? Can we understand how it works? But does it help us do the things we want to do? Because the goal of at least the computing that I'm interested in is actually helping people do things, right? Not just, proving a theorem or, getting some accuracy. But the idea of the causal models originally was because I think it's going to help us make interventions and do these other sort of tasks. So I'll stop there. Hopefully we still have some time for questions, I think.